Today we're going to introduce stoichiometry, and in the McGraw-Hill book, this is chapter 7. So chapter 11. If you have the PowerPoint notes for it, that'll help you out. Those will be up on the screen, but it's kind of hard to see on the little corner shots that you get. So first of all, you should know the definition of stoichiometry, since we're going to be doing this for the next week or so, and we'll be using it all year. Stoichiometry is the calculation of chemical quantities using balanced equations. And a couple of things important there. One is that we're saying balanced equations. Every equation you use in this chapter has to be balanced. Now, you may get some that are balanced already. Great. Check it. You're done. But if it's not balanced, then balance it. And remember, this is kind of a compendium, or it's all of the chapters we've done in the last month or so, all coming together as one, because we're going to need to name compounds, ionic and molecular. We're going to need to balance equations, and we're going to need to be able to do mole calculations like last chapter. So all of those things are important. Remind you of a couple of things. When you see a compound, and let's say you get a word sentence, like some of our problems are going to be a word problem, it's going to say magnesium chloride, and you need to be able to write MgCl2 instead of MgCl. And how do we remember all of that stuff? Couple of reminders. Ion both sides. Remember, if it's a metal and a non-metal, then you've got one from both sides. You crisscross to write the formula, and to name it, you use no prefixes. Okay? For molecular, you've got two nonmetals. They're both from above the stair step, and you do use prefixes on those. So those are just some important points. As you go through the practice problems, try to do those from scratch without looking at the key, and that'll help you out. So, one of the important things, like we say, always balance every equation. We'll need to be able to translate, and one of the pages that's called Chapter 11 Tutorial, that takes you through the steps. The whole front page is about translating, and we'll need to be able to translate in moles, which is very easy because that's just basically saying the numbers and the names of the substances. In mass, that's using the periodic table to add up the parts, and we'll also need to be able to translate in terms of volume and numbers of particles, which would be like big scale, like remember 1 mole is 6.02 times 10 to the 23rd atoms, and we're going to be talking about representative particles again, but that's up on the next page. So there are three chemical quantities, or three quantities that are always conserved in chemical reactions: mass, atoms, and energy. And those are always conserved. What does always conserved mean? That means that the left side is always equal to the right. So when you're adding up the mass of an equation, once you have the left side, the right's got to equal that too. So that helps you calculate. As far as atoms, obviously that's what we do when we balance. We make the same number of atoms on both sides. So we'll move on. Representative particles. This is just a review of what we talked about last chapter and the chapter before. Make sure you know the three representative particles. For most elements, it's the atom. For molecular compounds, it's the molecule. And the hardest one is for ionic compounds, it's the formula unit. Most people say, or a lot of people say ion for that one, but it's formula unit. So as far as translating, here's an equation, and it's on your PowerPoint notes. Probably can't see the detail down here in the little corner shot, but 4 moles of solid iron plus 3 moles of gaseous, that should be a G on the PowerPoint, I think it says S, gaseous oxygen, produce 2 moles of iron 3 oxide. A little bit about what we just said, that's translating in terms of moles, and to translate it, you would just basically write that sentence out. That translates it. The translations will be sentences that are written that tell what the equation means in a certain sense. Now, why did we say iron 3? Remember that the cops and the mercury, that's the way we memorize that in our class. The copper, mercury, lead, tin, and then the block back on the periodic table, which is CrMn, FeCO, and even Ni, those are all together. Those have multiple charges. So when you name them, you have to use Roman numerals. So when we look at something like Fe2O3, how do we figure out that that actually was iron 3? We uncrisscross it, and the 3 goes back to the Fe, and the -2 goes back to the oxygen, and that tells us that it was iron 3 that made that compound. So, and you have to use Roman numerals when you write the name iron 3 oxide. Okay, so as far as translating that in terms of moles, we just did that. All you have to do is say the number in front, the word moles, and then the name of the compound and its state of matter. So I'm going to go through that one more time, and you could run through this as many times as you need to rewind and run through it if you need to get that. But if you've got it on your notes page, then you basically just look at that and maybe run mine through and then try to do it on your own, and then maybe run back through to check yourself. And this is also online. If you don't have a copy, you can print it off of landerson.net under Pre-AP Chemistry homepages, Chapter 11, PowerPoint A. So, as far as mole, 4 moles of solid iron react with, the plus you say react with, 3 moles of gaseous oxygen to produce 2 moles of iron 3 oxide solid. There you go. That's the mole translation. As far as mass, how do we do that? Well, we just add up the totals, and the way I tell people to do this, we're going to rewrite the equation here. 4Fe solid plus 3O2 gas produce 2 Fe2O3 solid. So I tell people, draw a bubble. Whenever you do mass, draw a bubble, and then find out what the bubble weighs. That's how we translate it. So for this one, iron is on the chart 55.8 grams. So basically 4 times 55.8, and you have your answer for the mass. So 4 times 55.8, and we get 223.2. And we just write that up above, 223.2. 3 times 2 times oxygen. Oxygen on the chart is 16.0 grams. You look underneath oxygen, it's 15.9999. We round that to 16. So 3 times 2, you use both numbers for mass, times 16 gives us 96.0 grams. When you add that plus that, you get 319.2. We actually probably, since we multiplied 4 times 55.8, we probably just have 223 grams here. But that's okay. We're not, on this one, we're not focused as much on the significant figure end of it. So this plus this adds up to 319.2 grams. And when we translate it, this is the way we'd say it. 4 moles of, back up, we're not doing moles. So 223.2 grams of solid iron react with 96.0 grams of gaseous oxygen, produce 319.2 grams of solid iron 3 oxide. So basically we're doing the same thing we did with moles. We're just substituting in the gram value instead of the word mole and the number in front. Finally, for representative particles. Well, for representative particles, and we're going to translate that one up underneath so that I have a little more space, you basically multiply the number in front times 6.02 times 10 to the 23rd. So for this one, this would be 2.41 times 10 to the 24th atoms of iron, because it's an element, and for most elements, atoms, the representative particle. And here we have 3 times 6.02, which would be 1.81 times 10 to the 24th. And this is a molecule, because it's O2. There's 2 nonmetals together, molecule. 1.81 times 10 to the 24th molecules of O2 react to produce 1.20 times 10 to the 24th formula units of iron 3 oxide solid. So, to say all this at one time, now we're going to translate it in terms of representative particles. 2.41 times 10 to the 24th atoms of solid iron react with 1.81 times 10 to the 24th molecules of O2 to produce 1.20 times 10 to the 24th formula units of iron 3 oxide. Now, I know that sounds complicated, but what does it come down to as far as the process for particles translating? We need to do two things. Take the number in front, multiply by 6.02 times 10 to the 23rd, say the name of it, okay, and the representative particle for that particular substance. For, remember, it's either going to be atom, molecule, or formula unit, and then the state of matter, solid, liquid, or gas. So, the final one, you'll notice down on the bottom we've got a different equation to translate because this one doesn't have all gases. To do liters, you've got to have all gases, or you've got to have gases in order to translate. We could actually translate this part of it in terms of liters because it's a gas, but we're going to do a different equation. So we have 2H2 gas plus O2 gas produces 2H2O gas. And we're going to translate this in terms of liters. So when we do this, we're going to have the number in front times 22.4 because 22.4, our three conversion factors from last chapter are up here, 22.4 liters in 1 mole. So if we have 22.4 in 1 mole, how many do we have in 2? 2 times that, right? So this will be 44.8 liters. 1 mole is understood when there's no number in front. This is 22.4 liters. And 2 moles, again, is 44.8 liters. So to translate that, this is the way you would say it. 44.8 liters of gaseous hydrogen react with 22.4 liters of gaseous oxygen to produce 44.8 liters of gaseous water. That's translating it in terms of volume. So we move on. As far as doing the math now in this chapter, we're going to start by talking about conversion factors. When I ask you, where do you get the conversion factor for this chapter, every time for stoichiometry, the answer to that is going to be from the balanced equation. And that does two things. It tells you where it comes from, and it reminds you, balance the equation. So we have that same balanced equation about iron up here, and we are going to start with that equation and look at what are some conversion factors that we could get from that. Well, so you're looking at that same equation with iron and iron 3 oxide. We basically take the number of moles of one and put it in a ratio of numbers to another. It's just like a ratio, like let's say we were making cookies. You had 2 cups of flour, 1 cup of sugar, 4 eggs. So that ratio of parts is 2 to 1 to 4. And we're just making a ratio like that when we do our conversion factors. Notice on the PowerPoint slide that we've got 4 moles of iron for every 3 moles of O2. It's just comparing the iron 4 moles, that for every 4 moles of iron, we need 3 oxygens. We also could do 4 moles of iron for every 2 moles of iron 3 oxide. There's 6 conversion factors we could do for this. We could say 3 moles of oxygen for every 2 moles of iron 3 oxide. All of these can be flipped also, so that we could take the inverse of it. Remember, the unknown is always on top, so whatever we're solving for is going to be on the top. We're going to start out with mole-mole problems, and for every method, the mole-mole problems, those are 2-step. But the way we're going to teach this with a method called the Texas 2-step, all of our problems will be two-step. We actually do a little bit of the work up at the balanced equation, and it saves us from having to make four-step problems because most people have more trouble with those. So for mole-mole problems, this is going to be just like last chapter. The steps, you need to write the known and unknown every time. Read the problem, write the known and unknown. And then you're going to draw 3 blanks underneath. So it's going to be blank, x, blank, equal blank. And the last blank is, of course, our answer. So these are all two-step problems with 2 blanks and an answer blank. And we've got a balanced equation, and we've got a practice problem. We're going to take a spin around on that one. So it says, try this. Given 8.5 moles of solid iron, and we're going to write that as our known. If you don't want to write that separately, well, then just circle it and put a K above it for known. So here's our unknown and known. For known, we're going to write we have 8.5 moles of Fe. The unknown in this case is how many moles of solid iron 3 oxide. So question mark moles Fe2O3. Then we're going to draw our blanks here, and we're going to put this, the known, down in the first blank over 1. This has got to be reflex for you. It's got to be automatic. Read it, unknown, known, write the known over 1, 8.5 moles Fe over 1. Cover the number and drag the units of the known to the next denominator. Those steps, all of that has to be automatic. And if you do those steps, the problem will be easy to solve. So we have moles of Fe on the bottom, and our unknown goes on the numerator in the second blank, which is going to be moles Fe2O3. And of course, that's going to be in our answer because once these guys cancel, once the known units cancel, all we're left with is our unknown units, moles of Fe2O3. So where do we get the values for this conversion factor in the second blank? Remember, for this chapter, we get our conversion factors from the balanced equation. So in the balanced equation, how many moles of Fe2O3? We've got 2. How many moles of iron? We have 4. That's it. That's setting up the problem for a mole-mole. So we have 8.5 times 2 divided by 4. You've got your calculator, punch that in. If you don't, you could always do 1/2 because 2 over 4 is 1/2. 1/2 of 8.5, which is 4.25. And since we've got 2 significant digits, we would round that to 4.3. Our answer is 4.3 moles of iron 3 oxide. So that's the mole-mole problem. And there are practice pages that have sheets and sheets of that. It'd be a good idea for you to work through as many of those until you get comfortable doing the method, so it's just second nature. Every time you do the same steps. Unknown, known. Write your known over 1. Cover the number on your known, drag the units to the next denominator, put the unknown in the second top blank, and then get the amounts from the equation. That's it. And it actually is easy once you've done it. I know it's hard until it's easy, but you can make it easy by doing practice problems. So we move on, and I've got the steps written out here, and that seems like a lot. These steps, if you'll follow them step by step by step, that's what I intended. There's steps here like write the unknown and known. You know to do that, but I was real clear in doing each thing that you have to do. If you'll follow those steps, doing problems, you'll have better luck doing your dimensional analysis. So we're going to finish up talking about the problems that have mass, particles, volume, and the only real difference here is that when we get to our conversion factor, the blanks, it will not tell you moles of something, it will tell you something like grams or liters. And all you have to do is go to the balanced equation, circle that, I say put a bubble around it, and figure out what the liters are for that quantity, or the grams. And we're going to do one, take you step by step through that, and there's lots of practice problems that have the keys worked out. My suggestion is listen to this and then go get some of those practice problems and try to work through as many as you can. At the bottom of the page, we have a practice problem. We're going to work through that one. Just going to erase this one, and we're going to use the same equation that we had before, and unknown and known. So here's the problem, and if you've got the sheet, you can read through it. It says how many grams, so our unknown is question mark grams of Fe2O3 are produced when we have 133.4 liters of oxygen gas. So remember, every problem, 2 steps, and we're going to provide a last blank for our answer. The known, 133.4 liters of O2. Cover the number, drag the units down. So we have liters of oxygen on the bottom. Only the units. Don't bring the number down. That's why we cover the number. Bring the units down. What do we put in the top of the second blank? We put the unknown units up there, which are grams of Fe2O3. So now, instead of going up to the balanced equation and getting the mole value, I need to go up and get the gram value for Fe2O3. And we calculated that earlier. If you wrote that on your paper, we put a bubble around the Fe2O3, and we add up to Fe2O3, and we end up getting 319.2. 319.2. So in other words, this conversion factor tells us that in the balanced equation, where we have 2 iron 3 oxides, we add all that up, it's 319.2. Then we look at the bottom and it says we need to translate the oxygen in terms of liters. Go up to your balanced equation. It says there are 3 liters of O2. How many liters are in 1 mole? Well, in 1 mole, there's 22.4. So how many would there be in 3? It'd be 3 times 22.4. And that gives us 67.2. Boom. That's it. Now we do the math on this. So what we have is 133.4 liters of oxygen, that's our known, times 319.2 grams of Fe2O3 divided by 67.2 liters of O2. When we do that, we divide all that out. I'll punch it real quick so you know the right answer. I would work it and punch it in on the calculator. Make sure you know how to do that. 133.4 times 319.2 divided by 67.2, and we get 633.6. We've got 3 significant digits down here on the bottom, so we need to round that to 634 grams Fe2O3. And that's our answer, would be 634 grams of Fe2O3. So there are lots of practice problems for gram to gram, gram to liter, liter to liter on the packets that I gave you. Work through as many of those as you can. It's got the key and the solutions on it, and that will be the easiest way for you to go through and do these stoichiometry problems. If you have questions, come in for tutorials. Good luck.